Well, hello there, good people of the internet, and welcome back to another episode of Quantitative Bytes. Before I begin, I just want to say thank you so much to all those of you that have subscribed to my channel since the previous video. We're up to 21 subscribers now at the time that I'm recording this, and you know, as I said in the previous video, that means so much to me, so thank you so much. It really does help and makes me feel more motivated to carry on trying to make quality content and interesting content for you. So, you know, thank you so much. And if you like this video, please remember to hit that like button and please remember to subscribe so you don't have to miss any future videos. I do try to make a video at least once a week. So yeah, subscribe, keep up to date. You never need to miss anything. Thank you. Anyway, what I want to talk about today is a slightly different class of fractal curve. So over the previous two episodes, we've been working with the turtle graphics class that we created before, and we looked at, first of all, we looked at how to do turtle graphics in C++, and we created a class to allow us to do that. And then we went on to extend that to create code that would produce von Koch curves and the famous von Koch snowflake. And in particular, we looked at how we could make the generator for that as generic as possible. So we created a specific generator class, and that then allowed us to go on to create not just the classic von Koch snowflake, but a whole range of other fractal curves, simply by changing some of the geometrical parameters of the generator. And the class that we created made it quite easy for us to be able to do that. What I want to talk about today is a different class of fractal curves. These are called dragon curves. I think they're just quite interesting, and the way that they're constructed is very similar to the von Koch curves, but then with some slight differences as well. So I think it just makes an interesting follow-up episode. So as with all the previous episodes in this series, we're using the SDL library with C++ in order to get some kind of a graphical user interface. So we're using that to create a window that we can then draw into so we can see the results of our work. Because we're coding in C++ and because the SDL library is very cross-platform, it should be possible to follow along with these tutorials regardless of what operating system you're using. So I run Linux, as you'll see when we move to the computer in a moment, but that shouldn't be any reason why, if you're running Windows or Mac, that you shouldn't be able to follow along these tutorials. As long as you have access to a reasonably modern C++ compiler, you should be fine. If you're using an IDE, an integrated development environment like Microsoft Visual Studio, that should work just as well. You can still follow along. Some slight differences about how you set up the project and things, but you know, I leave that to you. Because I run Linux, I just do things from the command line, so it's a little bit different. But the actual code itself should work the same. There really shouldn't be any problems. The website for the SDL library gives really good instructions and details on how to install that for different platforms, so you shouldn't really have any problems. I only run Linux, so I can't really comment too much about how to do that in Windows or a Mac, but I know it is possible. So yeah, so feel free to follow along, and please don't be put off if you see that I'm running Linux and you think like, ooh, I don't use Linux, so this is not for me. This is absolutely for anyone, regardless of what operating system you use, okay? One of the great things about C++ is that it is actually truly cross-platform. Anyway, so without much further ado, I think let's jump over to the computer and let's have a look at what we're talking about with dragon curves and see how we can go about creating the code to do that. So I'm going to start with the code from the previous episode, and we're going to make modifications to that. So if you haven't watched the previous episode, I would suggest that you go back and have a look at that. I'll put a link up here so you can go and do that if you wish. And you can follow through that and have a look, generate that, build up the code from there, and then come back to this episode, and then you should be able to follow along what we're doing. We are, however, that said, going to look at all of the code here. So to be honest, you could also just pause this video at the key moments, and you should be able to see all of the code that we're going to use, and you should be able to type it in and follow it that way. But I would recommend going back and watching the previous episodes first. I think that's going to give you a better understanding of what's going on. Anyway, so I think that's enough of an introduction, and we should jump to the computer and see what's going on. Okay, so this is the classic dragon curve drawn here to not too many levels of the recursion, and we can see it has the sort of classic dragon curve shape, which is really quite fascinating. And I think, if like the image that I had on the thumbnail for this video, the way different dragon curves will tessellate together without overlapping is really quite fascinating. And yeah, one of the really nice sort of properties of these. So what I want to look at is how are these actually generated. So this curve actually begins its life with a generator, much the same way as the von Koch snowflake did. So, but in this case, we start with a generator that simply looks like this. So we have a defined start point and an end point. So originally we have one segment or one line that goes from here to here, and then we replace that with two lines. We start with an angle of plus 45 degrees and then an angle of minus 90 degrees, and then we end up back at our end point, okay? And we reduce the length of each segment as we go so that the whole thing still fits within the original start and end point. At the next level, so this is generation 1, this is generation 2, and you can see what we've done now is we've replaced each of these segments with the same thing. So now we've rotated initially by minus 45 degrees and then plus 90, that takes us to here, and then we rotate by plus 45 degrees, which will take us to here, and then minus 90, which will take us to here, which gives us that shape. And then, just as we did with the von Koch snowflake, we're going to repeat that process for each of these segments. So this one we rotate by minus 45, which takes us to here, and then plus 90, which takes us to here, and so on. And you can see how that goes, and then we simply keep repeating that process more and more. As we increase the number of levels of recursion, we get more and more detail in our curve, eventually ending up with the image that we started with. So that is the basic principle of dragon curves, and that's what we're going to do. What I want to do before we start is just to recap a little bit on the material that we went over for the previous episode. So just a quick recap. This is the classic von Koch snowflake that we talked about before in the last episode and in the episode before that. And that was created, if you remember, by a specific initiator, which in this case took the form of an equilateral triangle, and a generator that looked like this. So over the last episode, in fact the last but one episode, we spoke a lot about the generator for the von Koch snowflake, and in particular we discussed the geometry of this and a way in which that we could make this as generic as possible by allowing the user to specify an unlimited number of nodes between the start point and the end point. So the start point and end point were specified and then fixed angles, and then the user could specify any number of nodes with an angle for each node between them to create not just the classic von Koch snowflake generator or von Koch curve generator, which is this one. They could create any shape generator that they wanted, which could be used then to create some really interesting shapes, really different things, and really some quite exciting looking patterns. So that's all good, but the one thing that I realized actually when I went to think about this a bit more is that it is possible to generalize this generator even further. So one of the things that I did is I fixed the initial lines from the start point and the line to the end point were not definable in the way that we arranged this before, which means that this specific generator cannot be used to create a dragon curve. But like I say, when I really thought about it, I realized we could do this much more generally, and that's what we're going to look at today. So with the code that we're creating today, it would be possible to use it to create the classic von Koch curve or von Koch snowflake if you really wanted to. But it's also possible to use it to make the dragon curve as well. So let's have a look at how we do that now. So this was the geometrical problem that we solved before. We looked at how we could use trigonometry to calculate what the edge length should be so that this shape would always fit between the specified start point and end point. And we determined that simply you just had to take the cosine of each of these angles and take the absolute value of that, and then you could calculate how many of these segments there should be, and then you could simply divide the length from the start point to the end point by those number of segments, and you would get the edge length that you needed, which was the step length of the turtle. So we're going to use exactly the same method now with a new generator class, which, as I say, is going to be quite a lot more generic. So if we consider just the generator, so this is the generator that we used for the von Koch curve that we've just been talking about, it allowed the user to specify two angles, one here and one here, that would then define the shape. So this one would be plus 60 and this one is minus 120, and that would then create the desired shape. What you could not do was do anything about this edge here or this edge here. These were fixed. And in order to create the dragon curve, we need to be able to vary from the beginning. And in fact, of course, to make this generator as generic as possible, really we want to be able to do anything we want between the start point and the end point. We don't necessarily want to have a fixed edge at the beginning and a fixed edge at the end. As I say, with this new class, it would be possible to recreate this shape if you want to, but it opens up a whole new range of possibilities. So what we want to be able to do is something like this. So as we saw when we looked at how the dragon curves are generated, the generator is simply a triangle here with an angle of plus 45 degrees from the start point and then minus 90 degrees, which then takes us to the end point. And our challenge then is simply to calculate the length of each of these segments or edges to make sure that this whole structure fits between the start point and the end point, but we can achieve that using the same geometry that we considered in the previous episodes. So that's what we're going to do, and the new generator class will allow us to specify anything we want between the start point and the end point, and will therefore be considerably more generic than the generator that we looked at before. So let's have a look at some code. Okay, so that's my terminal window, we don't need that. So this is the code that we have from the previous episode. So we're going to look at the generator class first. So I have gone ahead and I've copied the code from the previous episode into a new folder so that I can make changes to it without losing what we did before. If you've been following along, you should have this code, or feel free to pause this video at the appropriate points and you can type out the code that's here and you should be able to catch up with where we are. So in any case, this is the generator class that we created before, and we're going to make some changes to this. We're not going to start writing the whole class again. I think that would be a bit of a waste of time, but what we're going to do is simply change the header file and the CPP file for this class. So the first thing that I want to do, and in fact I realize I actually made a mistake here in the previous episode. Apologies, I didn't spot that before. What we're going to do is we're going to change it to QB Dragon Generator H, and we'll do the same here. So that becomes QB Dragon Generator there, and we change the name of our class to QB Dragon Generator. And then we need to change the definition of the constructor and destructor functions there. And that is everything that we need to do for that. Now I want to save that as a different file name. So I'm going to go ahead and do that now. Okay, so I've gone ahead now and saved that as qbdragongenerator.h. Okay, and there is one line that we need to add to this. So basically everything stays the same apart from changing the name from qbvkgenerator. We're going to add here at the end in our private section, add int m_sign equals 1 semicolon. Okay, and save that. We will see what that's used for momentarily when we come to look at the CPP code. So that is the only line that we're going to add. We've changed a QBVK generator there to QB Dragon generator, and the references here to that. Everything else stays the same. So let's save that. Now let's have a look at qbvkgenerator.cpp from the previous episode. Okay, so the first thing that we need to change, of course, is we're now hash including QB Dragon generator like so, and we need to change all of these definitions. So everywhere we have QBVK, we're going to change that to QB Dragon. So I'm just going to do that using copy and paste. Save a bit of time. And the destructor, there we go. And then we're going to change, let's actually just, no, well, that's all right, isn't it? Yeah. So there's QBVK, paste, QBVK there, paste. So all of the QBVK generators, we change those to QB Dragon generator. You don't need to watch me do this, I'm going to skip ahead. Okay, so as before, I've now gone ahead and saved that as qbdragongenerator.cpp, and I've changed all the references from qbvk generator to QB Dragon generator throughout the code. So let's have a look at what we actually need to change, and it turns out it isn't really very much. Everything here, the constructor, the destructor, set start point, set end point, and add node, basically stay the same. Well, actually not true. Add node, we are going to make a change. So add node was where we allowed the user to specify the different nodes, and we assumed initially that there would always be a minimum of 2 edges because we had the edge from the start point and the edge to the end point. That, however, now is no longer the case, so we don't need to make that assumption anymore. So we simply delete that, and we simply set the number of edges to the number of angles that the user has specified. Of course, this does mean that for this class to work, it is absolutely required for the user to specify some edges for it to actually mean anything, but that should be okay. Okay, so that's add node dealt with, and then we have one new function that we need to define, which is the setSign method. Back in qbdragongenerator.h, there was one method that we need to add, another public method which we're going to add here after add node. It doesn't really matter where we put it as long as it's in the public section, but we'll put it here, and that is of course set sign int sign, like that. Okay, two lines that we changed in QB Dragon Generator H. We added in void set sign int sign, and we added int m_sign equals 1 in the private section. Okay, so we'll save that. That's QB Dragon Generator.h, and then QB Dragon Generator.cpp. We're going to create a new function here after add node. Again, doesn't really matter where we put it, but we'll put it here after add node. So go in there, we're going to create void QB Dragon Generator : set sign, which accepts as input int sign, like so. And very simply, we are going to put m_sign equals sign. If we were being really proper about it, we would do some kind of checking to make sure that this is either 1 or -1. That's really the value that the only two values that are acceptable. But for now, we're not going to worry about that. I think we know what we're doing, so it should be okay. And I know people could criticize me for that. I know really that's bad practice, but you know, what we're interested in here is the dragon curve at the moment. Anyway, so that's add node, and we've added set sign, and num edges simply returns the number of edges. That stays the same. Get edge, that stays exactly as it is before. This accepts 4 pointers to floating point values as input and an index, and then it checks if the index is valid, and it returns in to the location specified by those 4 pointers the values, the start and end points of the edge specified by index. So, as you might have guessed, the compute method is where we actually really need to make some changes, because we're now going to do the computation somewhat differently. So first off, we reset any previously computed vertices. That stays exactly the same. We need to do something a little bit different here. So here, because we were assuming that the start point and end points had their own edges and things, we did things a little bit differently. What we're going to do is simply cut that code out of there and paste it into this block. Okay, so only in the situation where num edges is equal to 1, where we have exactly one edge or one angle specified, do we simply take the start point and end point. In fact, actually, when I think about it, what might make a lot more sense would be to replace this with less than or equals to 1, because if the user doesn't specify any angles at all, then that will still work. Yeah, I think that makes more sense. We'll go with that. And right, so here we go. So this is the part of the code that we wrote before that computes the edge length. Okay, we're not going to make too much of a variation to this. The one thing we're going to do is, just for the case of clarity, we're going to change the name of this from numsegs to length multiplier, like so. And we're going to set its initial value, instead of being 2, it's now going to be 0. So of course the initial value for the number of segments was 2, because we knew that we always had 2 segments defined from the start point and the one to the end point. And now of course we're no longer doing that. So this value initially starts from 0. Now everything here stays exactly the same, except we change this to length multiplier, like so. And we don't need to change that. That's the geometry that we calculated for how we can work out the number of segments, or indeed the length multiplier from before. You can check that out in the previous episode if you want to understand more about how that works. The initial length is simply using basic Pythagoras to calculate the length from the distance from the start point to the end point, so we don't change anything there. Edge length we have to change because we're now dividing by length multiplier. That is perhaps slightly confusing naming, isn't it? Maybe I should have called that length divisor, but never mind. Okay, now we need to make some bigger changes. Okay, so we have this code here. This computes the first edge from the start point to the first node. Now, because we're not making any assumptions about the first node any longer, we're no longer forcing the generator to have this fixed edge at the beginning. We actually need to change this. So all we need to do is to get rid of that bit of code. So what we do is we move our turtle to the start point, we make it point towards the end point, and then we set its length to be equal to edge length that we've just calculated. That's all that we need to do there. And we then go into our main loop. So this again loops through every node that is specified and puts the result into this variable current angle. And all we do is we set the start point for this edge. We don't need to change that. So we set the we get the position for the turtle, and we store that in mx1 and my1 respectively. We then rotate the turtle according to the current angle. This is all the code we did before. We don't change anything. We then step the turtle to the new position, and then we again store the coordinates, the position that the turtle is now in, into mx2 and my2. And then we simply loop through, and we do that for every node. And then finally, the last thing that we don't need to do is to handle that last edge. So we can simply delete that bit of code, and that is everything that we need. Okay, let's just tidy that up. There we are. Let's save that. So that's qbdragon.cpp, qbdragongenerator.cpp, sorry. So at the beginning, we've only made really very minor changes from the code that we had in the previous episode. And like I say, you know, feel free to pause this video at any point, have a look at this code, type it through if you need to, and take the time to understand what's going on. Refer back to the previous episode and the previous but one episode for a description of the geometry of the generator, and I think it all should make sense. Okay, so that is everything that we need to do there actually, so that's quite straightforward. So let's save that. Now, in order to actually make our code do anything, we do of course need to make some changes into CApp. So CApp is of course our class that actually handles our application. So if we look in capp.h, this is the code that we had from the previous episode. So what we're going to do, we don't need an initiator class anymore, so we're going to get rid of that, and we don't need to hash include it anymore. We do need to hash include QB Dragon Generator, so we change that there from QB VK Generator to QB Dragon Generator. And what we're going to do, we're not going to create that. We're going to make an instance of our generator class, which is QB Dragon Generator, call it m_dragon, semicolon. Draw edge function to actually perform the recursive drawing. So we don't need to really change that very much, except we're going to add one more variable to it, which is int sign. And other than that, everything stays exactly the same. So let's save that. We don't make any other changes. That was capp.h. So let's have a look at capp.cpp. Okay, let's go up to the beginning. In capp.cpp, we don't really need to change anything here. We're going to do, let's just change the window title though to Dragon Curves. Dragon Curves, there we go, quantitative bytes, okay. And we don't need to change anything there. Right, one thing I'm going to do, I'm going to change the size of my window from 644/80 to 1280 by 720, right? Because we have all these extra pixels, we might as well use them. Now, this is where things are going to get a little bit different, okay? So, where are we? We, first of all, we don't need any of that, so we'll delete that, okay? And we're going to set our renderer color to black. In fact, I think this looks quite nice if we set that to a kind of dark gray. So let's change that to 64, 64, 64 by 255, and we use SDL render clear to actually clear the window. We're no longer using an initiator, so we don't need to set that up at all. We can just delete that code. And we are going to set up our generator. Let me see. Yes, but we're not going to do those. So let's just delete all of that as well. The first thing that we want to do is set the draw color. Okay, we're going to use SDL set render draw color of p render as our pointer to our renderer, and we're going to set this to the nice orange colors 255, 128, 0, and an alpha of 255. Okay, and then we're going to set up the dragon generator. We go initially just for the default geometry, so we do mdragon.add node. The first angle, as we saw at the beginning, is 45 degrees. And then we do mdragon.add node minus 90 degrees, like so. And we don't need any of this. So this was the code we used before that looped through all of the edges of the initiator and applied the generator respectively. We're not going to do that. What we're going to do instead simply is going to draw the curve, and we're going to do that, let's put a full stop there, we're going to do that by simply calling our drawEdge function, and we're going to pass our start point and our end point, the number of levels and our sign. So initially our start points are going to be 440f by 360f, and we're going to go to 840f, 360f. So a horizontal line from x of 440 to x of 840, and initially let's go for level 1 and put sign of 1. Okay, so that's everything we need to do there. The last thing that we need to do, of course, is to modify our drawEdge function. So that's this code here. We need to add here int sign, because we're now accepting the sign. Okay, we decrement our level exactly as before. Actually, we don't need to make very much change to this. We have one addition here, which is to set up a local variable to handle the sign. We're going to call that int sign2, and it's going to start at -1. Okay. Now, exactly as before, we set up arrays to store the points for all of the edges, because we're going to use the turtle to construct the edges and then simply store them. As before, we also set up these variables so that we can retrieve each edge. And these don't really change, except we just change this from VK generator to mDragon. Okay. We change that one, mDragon, oops, and mDragon, like so. So we do mDragon.set start point to x1, y1, and mDragon.set end point x2, y2. x1 and y1, x2 and y2 came from the input to this function. And then we call the compute method. And just before we do that, we need one addition, which is mDragon.set sign, and we need to set it to a value of sign. That was the variable that was input to the function there. And then we call compute, and that will, as we've just worked on the compute method and we've just seen that, that will actually go and generate the geometry that we need. And we then loop through each edge of the generator and extract and store the start and end points for each edge. So we don't need to change any of this code. This is exactly the same. Okay. And then we have our draw code. So if, just as before, we loop through each edge of our generator, so we need to change this from mvk generate. Oh, in fact, we do need to make a change here. I'm sorry. Yes, my apologies. In this loop, of course, we are looping through. We changed the name of our generator to mDragon, so we do need to change that. So that becomes mDragon, like so. So we loop through each edge in mDragon, and then we get each edge from the dragon generator, and we store the coordinates respectively. And then in our second loop, we change that from VK generator to mDragon, like so. And we now simply, if level is equal to 0, so this is our recursion element. So if level is 0, we can't do any more recursion. So then we actually do our rendering, and we draw a line between edge x1, edge y1, and edge x2, edge y2. Okay, that's really straightforward. If, on the other hand, level is not already equal to 0, then we recursively call the drawEdge function, and we pass to it each edge from our previous generator respectively. So edge x1, edge y1, edge x2, edge y2, all indexed by j, and we pass level, and we need to pass sign 2. And then one final thing that we need to change after doing that, we need to invert the value of sign 2. So we do sign 2 multiply equals -1 semicolon. Okay. And that is absolutely everything. The rest of this code is just the standard CAP code that we've been using since we began using the SDL library. If you want to know more about that, you can go back and look at the episode specifically on using the SDL library. And there we go. That is everything that we need to change. So if we go ahead and save that, if we go now to our terminal window, let's just clear that, have a look at what we've got. So these are the files that we have. Now, we haven't used a QBVK initiator. We're not using QBVK generator, but we can leave them there. It doesn't hurt. We've created our new class now, a QBDragon generator, which we've created. And so we have QBDragonGenerator.cpp and QBDragonGenerator.h. And we've created that simply by changing the code that we got from QBVK generator. And we've made changes to CAP as well, but we haven't changed anything else, so we should be good to go. So if we run our compiler, we want g++ -o main, compile main.cpp, cap.cpp, and what's next? QBDragonGenerator.cpp and QBTurtle.cpp. That's everything we need, and we just tell the linker to link against the SDL library. and let's go. And that worked, which is good. So no errors in our code. That's really good. This is one of the things that will be a little bit different if you are running in an IDE. Of course, the way you go about compiling the code will change a little bit, but not too important. Okay, so let's run that and see what we get. And there we go. That is the output of our code, and we see that is exactly what we expected for generation or level 1 of the dragon curve. So if we close that, let's increase our number of levels. So in capp.cpp, and where we created here, so draw edge, so we increase our number of levels. If we set that to 3, let's have a look what we get. Go back to our terminal window, rerun our compiler, and run our code. Okay, that's not right, is it? Okay, so if we look at generation 2, now we see that that isn't actually right. We have created we have a little bit of a problem there. That is not the shape that we wanted. So let's just have a look at our code and see what's going on. That's likely to be a problem in draw edge, I think. Okay, so it turns out that the problem is actually in where are we? In qbdragongenerator.cpp, and the reason that we're not getting the right results is to do with this line here, where we rotate the turtle according to the node. And the reason that is because we have not taken into account the sign. So we went to the effort to add the function so we could set the sign, and we added the m_sign member variable, but actually I forgot to really use it for anything. What we need to do here is simply put n sign multiplied by current angle. So we know that m sign is going to be either 1 or -1. So what you can see is that means that it's going to affect which direction we rotate in. So we're going to rotate left by either positive current angle or rotate left by negative current angle, depending on the value of m sign. And that's what allows us to create that kind of alternating rotate left, rotate right, rotate left, rotate right structure that or pattern that goes on to create the classic dragon curve structure. So if we go ahead and save that, now let's go to our terminal window, and if we run our compiler now, okay, and then run our code, yes, we now see that we get the kind of result that we want. So that is the level 2. So this is just like the examples that we showed at the beginning. And if we go back to our code, we're going to look in capp.cpp, and we can now look at the level 3 generator. So if we save that and compile and run our code again, now we see exactly the right result. We see that we get that for level 3. And let's just put this right up to something. If we make it level 10, and let's compile that, and let's see what we get. Okay, and that is the dragon curve, 10 levels of recursion. We see we get quite a lot of detail there. It's really quite an interesting curve, to be honest. We can go higher if we put it up to 15. Let's just have a look at that. Yeah, so when we put that up to 15, then we really start to see the shape of the classic dragon curve pattern, which I think is really kind of cool. It's really quite an exciting kind of pattern, and it gets very cool if you plot multiple versions of it together from, say, the same starting point but in different directions. But I'll leave that as an exercise for you to do. But you saw an example of that in the thumbnail image that I used for this video, which had 4 of these curves drawn together. And yes, you see how they fit so tightly together without overlapping is really kind of cool. But yes, really interesting. Now, there's several things here that are quite interesting. Now, one thing I mentioned is at the beginning is that we could, if we so wished, use this to recreate the classic von Koch curve. So what I want to do is just have a look, a demonstration of how exactly we can do that. And all we have to do is redefine our nodes. So to do the classic von Koch curve, we just set add nodes. We set our first one to 0 degrees, so no rotation. So that will just head towards from the start point towards the end point. And then we set our next node is going to be plus 60, and our next node is going to be minus 120. Now, if you've seen the previous videos, you will recognize these angles as belonging to the classic von Koch curve generator. And then we need finally plus 60f, like that, plus 60f. So we need to define an extra 2 angles if we're using this generator for the von Koch curve. And finally, because the von Koch curve doesn't have any of the inverting, we need to comment that out. And we also need to, we need to change this here. So int sine 2 equals -1, just change that to int sine 2 equals 1. So if we save that, and now we go, let's compile it and run our code, and there we are. And you can see that in this example now we get the classic von Koch curve drawn between the start point and the end point. So that's really a nice demonstration of just how flexible this new generator is. So the new generator really allows us to create a much wider variety of curves from different families. So we can go from the classic von Koch curve that we saw before all the way through to the dragon curve. And there we go. That's actually everything that I wanted to talk about today. So we've seen how we can create a much more generic version of the generator class that we created in the previous but one episodes. And this new generator allows us to create curves from both families. So we can create not only the classic von Koch curve, and we could, if we wanted, create the classic von Koch snowflake that we did in the previous episode using this new generator, but we can also use it to create the dragon curves as we've just seen here, which is a completely separate family of fractal curves, and I think they're really quite cool and quite interesting. And I think this is sort of just, it's one of the things that I really love about coding and about programming, is how it's possible to go from basically nothing. All we started with was with C++ and the SDL library, and we can just use the power of our minds to go and create code that does something, that creates something interesting, you know, like the classic dragon curve here. And I think that really is one of the things I love most about coding, is it really gives you that freedom, that flexibility to just go out and create something, and you don't need a lot in the way of, you know, resources and things to start with. You can really just go out and create, and I think that's really good fun. Anyway, that's, as I say, that's really everything I wanted to talk about today. I just want to reiterate what I said at the beginning, that, you know, thank you so much to the 21 of you that have subscribed to my channel so far. I really appreciate it, and yeah, you know, thanks. That means a lot to me, and you know, it's really motivating and helps me feel motivated to keep making, hopefully, interesting content. Let me know in the comments below what you think of this video and or any of the other videos on my channel. Or if there's anything in particular that you think you might want me to do next. You know, if enough of you suggest it, then maybe that's something we can look at. Otherwise, if you've liked this video, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't miss any future videos. I do try to post about once a week, so, you know, lots coming up and lots not to miss. If you go ahead and subscribe, then you don't have to miss anything. So yeah, I mean, look, it's been a pleasure. I really hope you've enjoyed this video. I've certainly enjoyed making it, and I hope you get something useful and a value out of it. And yeah, it just leaves me to say thank you very much for watching. It has been a pleasure, and I really look forward to seeing you in the next video. Bye.